Thank you very much. Always a pleasure to hear Mike talk. He talks about things that are hundreds of years old, and I'm going to talk about a few things that are millions of years old. Like many of you, I've drank out of Miner's Spring, and there's nothing wrong with me. I'm glad to hear that the arsenic isn't at the level that's dangerous. So these captivating titles that we have for our talks are always made by Jack Pennington. And he said, Wayne, why don't you talk about the uplifting story of the Colorado Plateau? So there you see the rocks uplifting very appropriately. And we're going to talk a little bit this morning about uplift. And uplift plays an oversized role in the formation of the Grand Canyon, but it's often overlooked compared to other canyon-related features or processes, especially for myself. I'm a sedimentary geologist and an earth historian, and I got hepatitis A from eating bad fish in Mexico during my semester of structural geology, and so I'm a little bit impoverished when it comes to structural geology, but nevertheless, uplift does play a very important role in the formation and what we see in the Grand Canyon. And this morning, we're going to talk about these 6 periods of uplift. We'll spend some time with those, so if you don't get to write them down right there, you're going to see that slide again. Uplift causes erosion in certain places, which yields sediment for other rock layers. So even though when sediment is deposited in the Grand Canyon, there must be some uplift somewhere that's producing that sediment. It also causes and explains the presence of unconformities. And if you've noticed on the trail, a lot of your guests always have questions about the great unconformity and many other unconformities that you might talk about. Unconformities represent periods of gentle uplift to cause these gaps in the rock record. Uplift gives the Colorado River the power to incise, so when we raise these layers up from where they were deposited, then the river responds by cutting down into those layers. It also places landscapes at elevations that increase precipitation, and this facilitates erosion. So the uplift of the Kaibab upwarp is a very important part of the story of eastern Grand Canyon. And uplift is likely linked with the volcanism that we see in western Grand Canyon. And we're going to talk about all of these here. So with respect to uplift causing erosion yielding sediments, this is a view from the South Kaibab Trail, and there's the first layers of rock that you see going down the Kaibab. Now, every single one of those layers, that sediment did not form where we find it now. It's been brought into the area that is now the Grand Canyon. And if we just look at one of those layers, the Hermit Formation, that material originated in one of the most interesting parts of the plateau's history, and that's the Ancestral Rocky Mountains. This was a mountain range that was uplifted beginning about 315 million years ago and lasted until 165 million. They're given the name Ancestral Rockies because they're located where the modern Rockies are today, but they were completely flattened and covered by the ocean before the modern Rockies came in. Well, that sediment that we see in the Hermit Formation came in rivers out of the Ancestral Rockies and came to coat northern Arizona, all the way down to the Mogollon Rim. And when you're in Monument Valley and you see the aprons of the monuments, that's the Organ Rock Formation. That's also part of the same thing. And the Cutler Group near Canyonlands. Uplift leads to incision by the Colorado River. And I think this is the one part of uplift that people most recognize, is that the river has cut down into an uplifted terrain. And if you ever take your guests on the Clear Creek Trail when you're camping at Phantom, you can get a view of this part of the Grand Canyon looking into what John Wesley Powell called the Granite Gorge. This is the most recent part of Grand Canyon to be carved, perhaps in just the last million years, but again, the result of uplift that happened prior to the incision by the river. And I'm always just so impressed when I get this view and you look and see how that river has been able to chisel through that hard rock. It's just amazing there's not more bedrock rapids along the Colorado River. The Colorado River has already done its work carving through this uplifted mass, and most of the rapids are from the debris that comes in side canyons. Uplift places landscapes at elevations that increase precipitation to facilitate erosion. There's the Kaibab upwarp right there, and you can see that green color for the vegetation. And the rock layers are the same, but this is about 2,500 feet higher than the same rock layers over here, because this giant blister on the Earth's crust, which we know as the Kaibab upwarp, you might know it as the Kaibab and Coconino Plateaus, but to a geologist it's an upwarp. That's a blister on the Earth's surface that the Grand Canyon is carved into. And it's fair to say that without that single blister there, the Grand Canyon would not be as spectacular as it is because of that extra 2,500 feet of uplift right in that area. And then uplift is associated with the volcanism in western Grand Canyon. And the heat associated with it likely did that. You can see a volcano erupting cinders on the rim of the Grand Canyon right there. How spectacular would that have been just a few 100,000 years ago to see that volcano erupting there? And there's a little riffle on the river called Lava Falls. I remember when I first moved to Grand Canyon, the thought was that maybe that was a remnant of a lava dam, but that's just like most other rapids in the Grand Canyon, big boulders coming down Prospect Creek and forming a little boulder dam across the river. So what causes uplift? And by the way, this talk is geared for those of you that are trail guides, maybe river guides, so that you can share some of these stories with your guests as you come down. Crustal collisions produce uplift. And so when two pieces of crust come together, it's like two cars running into each other head on. And you can see the crumpling that goes on there. This is probably the biggest, most modern crustal uplift where the India subcontinent has crashed into the southern underbelly of Asia and created Earth's highest mountains. And I was fortunate in 2007 to do a trek to the Everest base camp and got to see just how spectacular these mountains are. I was standing at about 18,000 feet here looking down into the clouded valley that we had taken 9 days to walk up. And we got this spectacular view of Mount Everest at over 29,000 feet. Now, the rock that sits on top of Mount Everest is a marine limestone that was deposited about 400 million years ago. But those rocks have been uplifted to this position right here. And I have to tell you, as spectacular as the mountains were, what was really most spectacular to me anyway was how deep the valleys were. And when you get uplift, you get this incision down into the rocks. Now, large-scale collisions can cause horizontal compression of the crust. So here we have a piece of the Earth's crust before there's a continental collision, and then as soon as the two things collide, we shorten the crust horizontally, and then we thicken it vertically. And that's how mountains grow, in this way. We just squeeze these two bits of brittle crust together, and they can actually deform in that way. So compression grows mountains not only upward, but also downward. And as I was telling you about the Himalayas, as erosion wears the mountains down, the overlying mass is removed and the mountain root rises from below. So if you look at the bottom diagram here, this is where the mountain top used to be, but when you remove all of that material off of the mountain, then the root actually pops up itself. And I've put this yellow dot over the same rock all through these 4 diagrams right here. And this is how rocks that were once deeply buried get back to the surface. And for our purposes in the Grand Canyon, this would be the Vishnu schist and the Zoroaster Granite. We're going to talk a little bit more about those rocks, but there you can see this picture of them at the mouth of Pipe Creek. These rocks used to be deeply buried, but because they were involved in a mountain building event, they got brought back to the surface. Plate collisions can also intensely fold and bend rocks. When rocks are buried, they become hot, they can become pliable, they can actually bend. And you can see the rock layers over here as they're bent, but this is a sheet of paper meant to show you just how incredibly rocks can be folded. And if you don't believe that rocks can be folded, look at this mass of rock right here, and that yellow line follows one individual bed that was brought up in a collision event. This picture is from the island of South Georgia in the South Atlantic. Subduction also produces uplift. Subduction is the process where a piece of ocean crust is shoved under the edge of a continent. And here in western North America, we had an ocean crust called the Farallon Plate, and it was moving to the east and got subducted beneath the western edge of North America. So we had this compression horizontally with the ocean crust and the continental crust coming together right there, and then we get this vertical thickening like that. And just on top of that, we can also start to melt that oceanic crust, and we'll put a few volcanoes on top of that thickened crust just to even produce more elevation in the mountain range. Rifting produces uplift, and this might be a little bit surprising because rifting is often where two pieces of crust pull apart, and so big blocks of rock drop down into the landscape. But if we look at this diagram right here, we can see that the rifting has occurred, but if you look at this block in the middle right here, it has a down-faulted arrow on that side of it, but an up-faulted arrow there. How can the same block have two arrows going in the different directions? Because those arrows on any fault are only meant to represent the relative motion from one side of the fault to the other. So if you were to just look at this fault right here, the right block went down and the left block went up. But here's the thing. Every block in that diagram went down. Some went down more than others. And when you come up to a fault in the landscape and you see something like this, you might think this block was uplifted. Actually, it was down-faulted. It just wasn't down-faulted as much as that one. And that's called relative uplift. And that plays into the story of the Grand Canyon supergroup. And there you see that big diagram again. The uplift that occurs with rifting is before the rift begins, there's a rift shoulder that develops, and the heat coming up from down below actually lifts the crust up to make sort of a dome right where the heat is rising up beneath it. Convection in the mantle causes uplift. The mantle is the layer of the earth that's directly below our crust, and when radioactive decay creates heat in the core, that heat escapes through the mantle, which is about 1,600 miles thick, and the mantle is under so much pressure and so hot that even though it's a solid, it can flow. And where you see these warm colors coming up, that's heated mantle material that can cause a rifting event at that point right there. And then you see the blue and purple colors here. That's where the mantle has become relatively cool, and it sinks back down to travel next to the core. And these concentric circles you see here in the mantle, it takes about 250 million years for one cycle to go through there. The mantle is convecting at about the rate your fingernails grow. And if you never cut your fingernails and you were lucky to live to be about 100 years old, your fingernails would be 8 or 9 feet long. So that's how fast the mantle moves down below the crust. Okay, so this is the uplift history of the Colorado Plateau, and what we're going to talk about first is something called the Yavapai Orogeny that created the Vishnu schist and Zoroaster Granite. A supercontinent was rifted called Rodinia, and that gave us something to say about the supergroup. And as I mentioned to you, unconformities in Paleozoic and Mesozoic rocks also signal some uplift. And then probably the three most important parts of uplift that if you only had time to talk to your guests about uplift for the more recent times, it would be the Laramide Orogeny, the Basin range disturbance, and recent uplift, something that's happened in the last 10 million years on the plateau. So regarding the Yavapai Orogeny, this is an outcrop right near the Black Bridge, on the south side of the Black Bridge, and you can see one of these Zoroaster Granite dikes that's been folded in a metamorphic event. The Yavapai Orogeny involves the addition of crust to North America. Way back at this time, the southern edge of North America was located right near the Wyoming-Colorado border, and big, long island chains of volcanoes were being brought in this direction. You can see the subduction is headed into that trench right there. This creates a line of volcanoes that is very long, and then the erosion on this and the continent will wash into this basin, and that's the origin of the material for the Vishnu schist. It's both sedimentary debris and it's volcanic debris that's washed into these basins, And eventually this block will collide right there at the yellow dot, which is the Shrine of the Ages at Grand Canyon, and that'll add real estate to Grand Canyon right there, or at least to the Colorado Plateau, the future Colorado Plateau. This is what these rocks look like. The Vishnu schist is always going to be sort of a gray or black color, and then the pink colors and maybe the white colors are the Zoroaster Granite. Technically, the Zoroaster Granite is slightly younger than the schist because the schist had to be there for the granite to move on up into it. And this all started with these volcanic islands that collided with North America. North America is off the diagram here, but here's the island arc that sits off. You can see these layers of sediment composed of sedimentary material and volcanic material. As these collisions occur, we create the Vishnu Mountains. And you can see all of this material right there. There's the surface of the Vishnu schist today, and the schist visible to us today formed 10 to 15 miles in the subsurface. And the reason we know it formed that deep is because of minerals that still exist in the part of the schist we can see right at the Great Unconformity. And today those minerals form at temperatures and pressures that could be found 10 to 15 miles down. And then we have this big period of erosion. Well, next we have the Zoroaster Granite coming in. And I can go back to that, can't I, Jack? Back button? I'll just experiment here. That back button. So there's the 10 to 15 miles of Vishnu schist that were eroded away from the schist we see today. And then the Zoroaster Granite comes in. That formed 15 to 18 miles in the subsurface. That was deep enough to melt the rocks, and those rocks rose buoyantly to invade the Vishnu schist. And that's how these two rocks got put next to each other. Uplift leads to erosion, so eventually that 10 to 15 miles was completely eroded away during about a 300 or 400 million year time period. That's about how long it takes to erode 10 to 15 miles of crust. And geologists are starting to identify a supercontinent that existed at the time of the Vishnu schist. They give it the name Nuna, and the red dot there shows you the Grand Canyon area during this time. Now, regarding the supergroup, this is a rifting event that happened. Hopefully all of you know that the supergroup is always found as tilted layers in the Grand Canyon, representing this rifting event that put those layers at that orientation. And this was the rifting of a supercontinent called Rodinia at about 750 million years ago, when blocks of crust that now belong to Australia and South China began to move away from the ancient core of North America, and that's the rifting event that occurred when those two blocks of crust moved away. By the way, when this happened, this was the birth of the Pacific Ocean. So this tiny little ocean that you see in here is going to become the Great Pacific that we know today. The supergroup is only found in isolated outcrops in the Grand Canyon, and that's why most of us find it so confusing. And I put the names of 5 major outcrops of the supergroup here, and it's not found everywhere in the Grand Canyon. And the reason for that has to do with this rifting event and the subsequent erosion, which I'm going to take you through right now. The supergroup was deposited, like all sedimentary rocks, initially horizontal. And that's how they originated, and that thickness was 2.5 miles, or 2.5 times the modern depth of the Grand Canyon. It's a huge thickness of sediment, but what happened is that we started to rift apart the Rhodinian supercontinent, and this caused uplift and tilting of the layers. And then what happened, the blocks were faulted and relatively uplifted or downdropped. Remember that diagram where I showed you they're relatively up or relatively down? You can see that right here. And it's also visible from the South Kaibab Trail as you're making your way down to Phantom Ranch. And there's one of these blocks here. And what you see in the photograph here mimics what's in the cartoon right on top. And so believe it or not, this is, I think, what makes it most confusing to people. The block that was down faulted is now topographically high, and the blocks that were uplifted had all of the supergroup eroded away before the Tapete sandstone came in. And there in the cartoon at the top, you can see this. This is shaded in there. The supergroup used to be up there in this upfaulted block, used to be here in this upfaulted block. Whenever we see the supergroup, that is a block that was downfaulted the lowest and was preserved during that period of erosion right there. And that's why the supergroup is not found everywhere in the Grand Canyon. All of these clear areas you see where there is no supergroup, those are areas where the blocks were uplifted and all the supergroup was taken away. And here's the route of the South Kaibab Trail down to Phantom Ranch, and you can see that it goes through one of these blocks of the supergroup. I must admit, a lot of times people have a hard time with geology, so if there's one story I'm going to leave out of my hike, it's going to be a supergroup story. Sorry to Carl and Lori about that, but the supergroup can be difficult to understand. I'm happy if people can understand that the Kaibab limestone was deposited at the bottom of the sea. I feel like I've been a success if that happens. So here's this second unconformity, and you can see those preserved blocks of the supergroup. In these areas right here, their blocks were uplifted, and so all the supergroup was worn away there and there. And then on top of that, we get all of the unconformities in the Paleozoic rocks. I'm just going to highlight these with lines right here. The red wall has some channel deposits below it and above it. The Supai group has unconformities all the way through it. And these are all gaps in the rock record where the Earth's crust was slightly uplifted such that it could not accept sediment from somewhere else, or perhaps was even slightly eroded, and they went away. And any of us that are lucky enough to go down the river, you can see some of these great unconformities down in the river. There's 3 different limestones in this photograph right here, the Muav limestone, the Temple Butte Formation, and the Red Wall limestone. And you can see that channel that the Temple Butte Formation is set down into. And if you want to know how old these unconformities are, it's 160 million years between the Muav and the Red Wall. And these little channels that you see right here are pretty rare in the Grand Canyon. So when you see that contact, as in most of the Grand Canyon, between the Muav and the Red Wall above, 160 million years represented there. None of the rocks are tilted or deformed in any way, and so it looks like it was just continuous deposition. Fortunately, fossil evidence and other dating methods can tell us how long that unconformity is. And there's the Pangaean supercontinent, where a lot of these Paleozoic unconformities were formed. And you can see that a couple of different crustal blocks that used to be their own mini-continents have welded together to form the continent of Africa and the continent of South America. So let's talk about the Laramide Orogeny. I'm sure this is what Jack had in mind when he said talk about uplift, because the Laramide Orogeny is probably, the Laramide may be the most important uplift event in Grand Canyon's history. That can be debated, of course, by geologists, but nobody disagrees that during this period of time, between 80 and 40 million years ago, that we had significant uplift of the Colorado Plateau. Also, we created the Rocky Mountains, the modern Rocky Mountains, for the first time. The Laramide is named after basin deposits that were washed into a basin near Laramie, Wyoming. And here's a state map of Arizona. And you can see a number of these Laramide age basins, the Denver Basin, the Laramie Basin, the Powder River, and the Bighorn Basins. And these are the uplifts that supplied the sediment for these basins. And so we're not naming the Laramide after the uplifts, we're naming them after the debris that was washed out of the uplifts. And many fantastic fossils were found in these sedimentary deposits. That's why early geologists recognized the importance of the Laramide in the western landscape. In this confusing diagram here, you can see where the brown and the green are located, mostly up in this area. These are big uplifts. The blue areas are the basins that were receiving the sediments off of the uplifts. And more important to the Colorado Plateau story are these lines with the diamonds on them. This is where we formed Monuc Lines during the uplift of the crust in this area. We have some spectacular Monuc Lines in the southwest. If you visited Capitol Reef, you've seen the water pocket fold, where these Mesozoic layers are folded. Closer to home, we have the Echo Cliffs, which is also a Monuc Line, a single flexure in the Earth's crust. And then in the Grand Canyon, we have the East Kaibab Monuc Line, where all the layers of the Grand Canyon are draped over a very deep fault. And if we were to look deeper into the Grand Canyon, we can see what's causing this Monuc Line. It's the Butte Fault. And the Butte Fault has about 2,500 feet of offset right along a line here, and it puts Tapete sandstone next to the Supai. I know there's a few people in the room that have hiked that. Is that my wife? No. Okay. I thought I could get lucky and score points, but obviously I didn't. Not with the rest of the people. So the river crosses this uplift right here. Here you see the Colorado River, and it goes right through this Kaibab upwarp. This is where the Monuc Line is located, right there. I've shown you that before. But the X represents where the crest of the upwarp is. That's the highest elevation. It's about 9,200 feet. By the time you get to the north rim, it's already angled down about 1,000 feet on the north rim right there. And it's interesting to think what the Grand Canyon might be like had the river carved its course in some other place across this uplift. And this explains why the north rim is 1,200 feet higher than the south rim, because the crest of the dome is back off the slide there to the right. But what about if the river had sliced the canyon on the north flank of the dome? Then the south rim would be higher than the north rim, and we'd be here on the south rim looking down onto the north rim like we do the opposite today at the north rim. What if the river had sliced the canyon on the crest of the dome, and then both rims would be the same elevation? So we can talk a long time about why the river was specifically placed where it was, but that's a different talk for a different year. What probably caused the Laramide Orogeny was that the Farallon plate that was going underneath the edge of North America had different segments to it, and most of the segments would go down at a regular steep dip, which is about 45 degrees, but there probably was one segment that was not going down as deeply, and when that oceanic plate was moving along the bottom of the crust, it tugged on the bottom of the crust and caused these uplifts to occur way inland from the continental edge. And you can see the shallow dip right here, and if you just trace it out, you can see that it actually forms the east and west boundaries of the Colorado Plateau. And it's possible that this shallow dip is what's responsible for that. Here's another way to look at it. You can see the Farallon plate there. This is that shallow dip that has gone under the crust, and geologists are able to even image remnants of the Farallon plate underneath Iowa and Missouri as it continues to move under North America. The Farallon plate going under the crust may actually explain the high elevation of the Great Plains, and that's something that's being discussed. In the last 20 million years, there's been a deformation event known as the Basin and Range Disturbance, and flying out of Las Vegas, you go over Frenchman Mountain. These are all of the Colorado Plateau layers from the Moenkopi all the way through the Kaibab and Toroweap and Supai, and you even get down into Vishnu Schist over here on the west side of Frenchman Mountain, and these whole blocks are being pulled apart. And if we were to look at the creation of the Basin and Range in the last few million years, look at how North America is just being stretched out there to the west. And the state of Nevada has been stretched about 100%. It's doubled its width from what it was just 20 million years ago. In the Grand Canyon, the Basin and Range Disturbance reactivated old faults, such as the Bright Angel Fault, which we can hike down when we come down from the North Rim. And this very long, straight canyon right there is a result of reactivation during this deformation event that started about 17 to 20 million years ago. And at the lower tunnel on the Bright Angel Trail, you can actually touch the Bright Angel Fault, where the Toroweap Formation and the Coconino Sandstone are put next to each other. And I always stop here with my guests and let them put their hand right on the fault line there on the uphill side of the lower tunnel. So don't allow yourself to go by this place again without showing people and having them touch the Bright Angel Fault. If you turn around 180 degrees from this spot, you can look back and then show them that long line of the Bright Angel Fault as it makes its way up into the North Rim area. By the way, this flat surface right here is actually the result of movement on the fault This is the block that went down relative to this one that went up. And by the way, the original Bright Angel Trail, I'll put this in for you, Mike. The original Bright Angel Trail actually went around this knob of Coconino sandstone. Very steep section right here. But when they redid the trail in 1935, they just blasted a tunnel right through that uplifted block here. And then recent uplift. This is the most recent period of uplift to happen in the Grand Canyon. And it probably is the result of action in the mantle. And this is from the book Carving Grand Canyon. You can see here that the crust and the upper mantle, they form a feature called the lithosphere, and it's thought that a piece of the lithosphere may have actually broken away or dripped down into this much hotter mantle, and they call it lithospheric drip. And what fills in behind from this piece that is broken down is all of this hot mantle material. When that hot material comes up right beneath the crust, it can cause the crust to be uplifted, and then you can also get the volcanism that will erupt out here on the surface. And this is one of the most recent theories on what's causing the uplift of western Grand Canyon, and all of this may be eating its way into other parts of the Colorado Plateau. So there's the uplift history of the Colorado Plateau. Some of those are more important than others, so if you were to talk about this on the trail, I'd probably concentrate on these, although I love telling a good Vishnu schist story about how rocks that were once 10 to 15 miles got back to the surface. Thank you very much. Are there any questions? Yes, if you're going downhill on the Bright Angel Trail, you will get to the fault on the uphill side of the tunnel. Yep, and I'll guarantee you, after you saw those pictures, you can't miss it. It's a big vertical line going right through the rocks, and Toroweep is on the east and Coconino is on the west. That's how much of the offset. It's about 150 feet of offset right there along the fault. The question was, why didn't the river go around the uplift? Why did it go across the southern flank of it? Damn you. Don't ask questions like that. It's probably likely that when the river's course was established, the upwarp was not a significant landscape feature for whatever reason that might have been. In other words, we see it today as an upwarp that sits 25 feet higher than the marble platform. But it could have been that when the river established its course, the marble platform had its layers still in place, and there could have been a very subdued surface that was beveled in across where the Kaibab upwarp is today. So you have to think in a sort of a different way. I don't think the upwarp really had much of a landscape influence or a topographic influence when the river's course was established. Although there's many, many different ways to explain it, that's just what we see on the landscape today, is that it's there. Yes, Brian. So the question is the idea that between 70 and about 30 million years ago, rivers in this part of the world were going from the southwest to the northeast. They were going in the opposite direction that the river goes today. And Andrei Potochnik, a geologist that Brian referred to, is a geologist who has done work on the Salt River down south of us, and he has determined that the Salt River was going in this opposite direction up until about 33 million years ago or 30 million years ago, and wanted to apply that to the Colorado River. The question is, what is the source of the water that went from southwest to northeast? And that would be that in the areas where Tucson and Phoenix and Kingman and Las Vegas are located today, those used to be the highlands, and everything here on the Colorado Plateau was the lowlands. And rivers would flow from southwest to northeast for this long period of time before we established the rivers we have today. And it's almost like the landscape has been inverted. Now we drive downhill to Las Vegas and Phoenix. Prior to the Basin and Range disturbance, you would drive uphill from here to Phoenix and Las Vegas. And that was the source of it. And before the Rocky Mountains came up, beginning about 65 million years ago, there were rivers headed from this part of the world probably all the way to the Mississippi. And then when the Rocky Mountains were uplifted, it caused freshwater lakes to form on the plateau surface. So the question is the change in plate motion due to the San Andreas Fault? And the answer is yes. Once the Pacific plate came in contact with western North America, the relative motion between the continent and the ocean crust was in a strike-slip manner, and that particular stress on the crust is probably what has caused the basin and range to open up like it has. But I'm going to stop you there, Brian, because you're too far ahead. I did that to massage his ego. Yes. What are the techniques that are used to sort of image those pieces of crust there? And I'm going to embarrass you, Carl, to please come on up here for a second. I'll introduce the idea, but essentially what you can do is you can take a CAT scan of the Earth's crust, and what you can do is you can send vibrations down through into the Earth, and depending on how hot the lower crust or the mantle is, those waves will come back at a certain speed. So they're able to make an image of hot areas below, that is where this upwelling mantle material is, and where the crust is thicker. And so they can actually make a map and show the hot areas, and they can show where the cool areas are. And it's very ingenious the way they do it. And this is just one of the many modern techniques that are used by geologists to sort of image things that we couldn't do 30 years ago. And I'm just going to introduce Carl Karlstrom, who's done a lot of work in this area, and he can probably elaborate a little bit more.
Yeah, so the National Science Foundation over the last 15 years funded the biggest experiment that geologists have ever done. It was called EarthScope, and we set seismometers. We put them across the U.S. Took years because we didn't have that many seismometers, but we put them in swaths. So started in California, and then they recorded for about 2 years or 3 years sometimes. And the thing that we're measuring is it's called natural source seismology. Some earthquake goes off in a big one, let's say in Indonesia, and those waves go down through the earth, and by the time they come up to North America, they're coming almost vertically. And so 2 different seismometers will record the arrival of that earthquake, which we know when it went off exactly. It records the arrival of that energy at different times. And so that gives us the velocity of the seismic waves through the earth beneath North America. So that's where we image the red areas, which are slow velocity, and the blue areas, which are high velocity, and that tells us about partial melt and the shape of the North American plate. So we always like to ask, does anybody know where the nearest plate boundary is today, if you're into plate tectonics, from where we're sitting, Shrine of the Ages? Well, you know, the San Andreas Fault, so Wayne mentioned that, but Jack knows this. That's right. So the North American plate's about 150 kilometers thick, and so this weakest asthenosphere underneath us, and that's the base of the plate, and that's this recent uplift that Wayne was talking about, probably driven by things pushing up, pulling down on the base of the plate. Could I make one comment? I think it's actually right when you're talking about the emphasizing the uplift of the Colorado Plateau and carving of Grand Canyon, to emphasize those last 3 episodes. And rocks were at sea level. This region was at sea level before then, and it's come up, and we argue about how much in each of the events. But I think we're getting lots and lots of evidence that they're sort of sub-equal. They're sort of thirds in terms of the uplift of the plateau, and getting across how the landscapes evolved in each of these uplift events is super interesting, piecing it together. And I think the breaching of the Kaibab uplift was probably in that middle one, and there was a Paleo Canyon that went across, and then there were early Paleo Canyons in the Laramide, and then north flowing rivers kind of along the Hurricane Fault. are as old as 65 million years old. So there's river systems and sediments that we're recording. Each of these uplift events that I think are coming into focus a bit. It's still piecing evidence together from really disparate places, but 3 episodes and different components of the landscape that we see now.
So I see I have a few minutes left. I'm just going to very quickly run through a short, thank you. And thank you, Carl. I'm just going to run through a quick summary of Grand Canyon's history from 2000 to 1,750 million years ago. We had this collision of island arcs to create the Vishnu Mountains and the Vishnu Schist and the Zoroaster Granite. And during this time, the Vishnu Mountains, that's where the future great unconformity is going to be. There's going to be 10 to 15 miles of rock that's going to erode away to give us the surface that the great unconformity sits on today. The Vishnu Mountains are eroded, and then we pile 2.5 miles of supergroup rock on top of that. When Rodinia splits up, those blocks become relatively faulted up and down, and then we have the lowermost faulted blocks only preserved on the landscape. That's the second great erosion. On top of that, we have the Paleozoic rocks, 4,000 feet of beautiful sedimentary rocks, giving us 4/5 of the height of the Grand Canyon. And then on top of that, not present anymore at the Grand Canyon, we have the Mesozoic rocks. And there could have been as much as 10,000 or 2 miles of sediment that used to sit on top of the Vishnu Schist and Zoroaster Granite. And eventually we erode it, and voila, the Colorado Plateau and the Grand Canyon cut into this. What a wonderful place we live in. And thank you all very much. I only saw one person asleep.